For this video, we are going to work on solving exponential equations. Now, if you think about solving a typical equation, it'll look something like this, where we have, 5x plus 2 equals 27, and our goal is to solve for that x. Solving exponential equations is going to be just like this, but it's going to look a little bit different, because instead of having our x down here next to the coefficient, our x is going to be in the exponent area, and we're going to have to solve for it. Now, if you are good at solving these kind of equations, part 1 is going to be pretty simple for you. Part 2 might be a little bit different, but with some practice, you'll be just fine. So let's get into our first example for solving exponential equations. So our first example here is 5 raised to the 2x plus 3 power, and we're saying that it has to be equal to 5 raised to the 5x minus 9 power. This may look confusing or difficult at first, but it actually isn't too terrible. Because, first of all, our bases are the same. We have a 5 here and a 5 there. For part 1, our bases have to be the same. So if you have a problem where the bases are not the same, we can't solve it yet. That's for part 2. Now, before we try to solve for our x's, I want you to think of this. Let's say I have 2x equal to 2x. Well, what does this mean? It means that whatever is over on this side has to give you the same number as this side. So if I divide by 2, I would get x equals x, and it turns out, no matter what I put in, I'm going to get the same value. Well, with this side, whatever we put up here, whatever it becomes, 5 is going to be raised to that power, and, well, we have to get it to be raised to the same power on this side as well. So you might be wondering, well, how am I supposed to do that? And here it is. If the bases are exactly the same, all we have to do is take this exponent, 2x plus 3, and set it equal to this exponent, 5x minus 9. So we'll say 2x plus 3 equals 5x minus 9, and now we can go about and solve it algebraically. I have to subtract 2x from both sides. I have to add 9 to both sides. And we end up with 12 equals 3x. Then divide by 3, and we get x equaling 4. So our answer is x equals 4, and what good does that do us? Well, if we plug that into our original equation, let me erase this so we have some room. If I plug that into here, 2 times 4 is 8, plus 3 is 11, so this side becomes 5 to the 11th power. And if I plug it in on this side, 5 times 4 is 20, minus 9 is 11. So this side also becomes 5 to the 11th power. And if we're up to date with our identity property, you can say something is always equal to itself. So it works out. Since these bases were the same, we were able to take this exponent, set it equal to that exponent, and we could solve it. That is part 1 in a nutshell. Let's try a couple other examples just to make sure we've got it. For our second example here, we have 4 raised to the 3x minus 2 power, and we're setting it equal to 4. And this is a little different from our last example because you could be thinking to yourself, there's no exponent here. They have the same base, so I can do what I did last time where I set the exponents equal to each other, but there's nothing over here. Well, think about it. If all you have is a whole number, what's the exponent? That's right. It's automatically a 1. If all you have is a number, the exponent is 1, and since it's 1, it's generally not written. So we have 2 exponents. We can set them equal to each other to solve for x. 3x minus 2 equals 1, and this is actually a simpler algebraic equation than the last time. If I add 2 to both sides, I get 3x equals 3, and then divide by 3, and we end up with x equaling 1. Now, we should probably check just to make sure that it works out properly. If I put 1 in for x here, 3 times 1 is 3, 3 minus 2 is 1, so this side becomes 4 to the first power, which is exactly what this side is. So it works out. Excellent. Alright, let's try another. For our final example, we have 4 raised to the x minus 5 power, and we're setting it equal to 5 raised to the 2x plus 1 power. Hopefully, based on what I've said earlier in the video, you're saying to yourself, hey, you said we can't solve this. And you're exactly right, we can't. We're not going to solve this in part 1. And even if we were to go to part 2, we won't see something this advanced. This is a little more complicated. So the fact that this base 4 is different from this base 5 means we're not going to be able to solve this right now. We could, if we forgot about that, we could still do what we were doing before if we would decide to go on autopilot. So if I took my x minus 5, set it equal to 2x plus 1, if I subtract x, and I subtract 1 from both sides, those cancel out, and we have negative 6 equals x, we still get an answer. X equals negative 6. But it's the checking part where we discover, hey, this actually doesn't work out. Because if I put negative 6 in here, negative 6 minus 5 is negative 11. So we have 4 to the negative 11th power equaling, and if I put negative 6 here, we're going to get 2 times negative 6, which is negative 12, plus 1, which is negative 11. So we get 5 to the negative 11th power. And while their exponents are the same, their values are not. 4 to the negative 11th power is not the same thing as 5 to the negative 11th. So these two do not equal each other, and this did not work. So there you have it. This is part 1 of solving exponential equations. Main key points to remember: your bases have to be the same. And as long as they are, you can set your exponents equal to each other and solve for x. Good luck.